Okay. So we'll talk about electromagnetic waves. Let me show you an example. As you guys know, electromagnetic waves are waves that have electric and magnetic fields in them. Okay. And to create electromagnetic waves, what you need to do is, so let me show you a simulation. Okay, so we'll look at a simulation for creating electromagnetic waves. So let's go to go here. All right, there you go. All right, so there is the Java file. And to create electromagnetic waves, all you need is a charged particle. Okay. And what you need to do is take a charged particle and make it oscillate. I mean, make it accelerate. And the easiest way to make a charged particle accelerate is make it oscillate. Okay, so there you go. You grab hold of an electron or a proton and jiggle it. Okay. And what you do is you end up emitting electromagnetic waves. What is shown here is just the electric field. And you see this electric field, if you have a metal rod somewhere else, that's an antenna. And this electric field will make the electrons in this rod move. So you're generating an electrical signal. Okay. So again, to produce electromagnetic waves, what you need is a charged particle. You need to accelerate a charged particle, which will send out electromagnetic waves. And these waves, all waves carry energy, okay? And you see the energy carried by these electromagnetic waves can be deposited in this antenna, okay? So you're transmitting a signal, you're transmitting energy without, through perfect vacuum, okay? So you can do this through perfect vacuum. Now this idea is general. So for instance, if you wanted to emit gravitational waves, what you'd have to do is not take an electron, but take a massive object. An electron would emit gravitational waves too, except that they would be too weak. But if you grab hold of a black hole and jiggled it like this, you would emit gravitational waves. Anyway, we're talking about electromagnetic waves. So what you need is a charged particle accelerating, which will emit electromagnetic waves. And this chapter is about these electromagnetic waves. And you guys know of various kinds of electromagnetic waves. Light waves are electromagnetic waves, infrared, UV light, X-rays, radio waves, they're all electromagnetic waves. What is different about them is their frequencies and wavelengths are different. All right, so let's go through the slides. All right, so so here are the 4 Maxwell's equations. Like we've said, Maxwell's equations summarize all of electromagnetic phenomena. And what these equations, these are differential equations, these equations tell you what will produce these fields. So electric fields are produced by electric charges, and electric fields are also produced by time varying magnetic fields. Okay. This equation tells you magnetic fields are produced by moving charges as well as time varying electric fields. Okay, what this equation is telling you is, okay, so this equation tells you that you can, well, in nature you can get positive charges by themselves or negative charges by themselves. This equation is telling you that in nature, if you have a North Pole, you'll have a South Pole with it. You'll never find them isolated. So anyway, that's what this equation tells you. All right, so here are the equations that are, these are the four Maxwell's equations, okay? And this is called the Lorentz force law. And what this equation tells you is the force on a charged particle, okay? So these equations tell you charges and currents produce electric and magnetic fields. And what this equation tells you is electric and magnetic fields influence charges, okay? Static charges and moving charges. So again, charges produce electric and magnetic fields, and magnetic fields and electric fields in turn influence charges, okay? Anyway, those four equations, from these four equations, you can derive all of electromagnetic phenomena. Okay, so what I'll do is I'll write down these equations in vacuum. What that means in vacuum, you don't have any charge distribution or current distribution. So in vacuum, these two terms will go to zero because we'll be interested in solutions to this equation in vacuum. Okay, so let me write that down. All right. Let's see. Let's go to the chalkboard. Okay. So the vacuum equations. The Maxwell's equations in vacuum are these. Okay. Okay, and you will see that c squared, the speed of light, is 1 mu naught epsilon naught. So this equation becomes 1 over c squared del E by del T. Okay. Okay, so there are the vacuum equations, and we'll use them in a second. Okay. So let's go back to the slides. Okay. So again, let me show you the simulation. What you want is, so this shows you how to produce electromagnetic waves. Let's decrease the amplitude a little. Okay, so you jiggle a charge and this will emit electromagnetic radiation. All right, so we are interested in these electromagnetic waves. And it turns out that these equations, okay, so the existence of electromagnetic waves were predicted by Mr. Maxwell even before we experimentally confirmed them. Okay, so these equations predict the existence of electromagnetic waves. And so that's a pretty neat thing. Our equations are predicting something, and that's what, and then we went looking for them. Okay, so let's derive that equation. And let me show you one thing you'll need for that equation. By the way, these are, so here is an AC current, that's a charge jiggling in that antenna that we're seeing. And this is how the electric fields and magnetic fields look like as they're propagating away. Okay, so here is the integral form. There is Faraday's law. Okay, and so time varying magnetic field. These fields, magnetic fields changing in this direction will produce electric fields like that. That's what this diagram is showing you. And what this diagram is showing you is time varying electric fields like this. Electric fields like this will produce magnetic fields like that. Okay. So this is the electric flux. But anyway, we won't worry about that. So here are the four Maxwell's equations. We are interested in them. We'll look at solutions to these equations in vacuum. So this term will be 0 and this term will be 0. And I wrote those equations. So Maxwell, using the four equations shown, predicted the existence of electromagnetic waves that propagate through vacuum at the speed of light. Okay. So Maxwell predicted the existence of these electromagnetic waves. So let's look at what we need. So here is the next thing we need to derive the wave equation. So what this equation says is, again, you will see this in Calc 3 if you haven't already. But here, this is the equation we need. And you can prove this for, so you can prove this identity. What this identity says is the curl of a vector field, curl of curl, is equal to gradient of the divergence of this vector field, okay, minus del square A. That's the Laplacian, okay. And so let's use that. So I'm going to so we'll use that, and I'm just, all right, so let's go to the chalkboard. Okay. So here that vector identity, what we're going to do is we're going to apply this to that equation, okay? So what we'll do is we'll take curl of E was equal to minus del B by del T. We'll take the curl of both sides of the equation. And the curl and the time derivative operator commute. Okay, so that's the equation. Now this guy is gradient of divergence of E minus del square E. By the way, del square, the operator del square is del square dx square plus del square del y square plus del square del z square E. Okay, that's what that operator is. And that's equal to minus del by del t of curl B. Now you can see curl B from this equation, curl B is 1 over c squared del E by del t. Okay, so curl B is del E by del t from 1 over c squared del E by del t. This is 0. This term is 0. Divergence of V is 0. In vacuum, that is 0. Okay, so this term is 0. So what we have is minus del square E equal to 1 over c squared del minus 1 over c squared del square E by del t squared. Okay, so this is equal to del square E 1 over c squared del square E by del t squared. Okay, and this is the wave equation. Okay. So here's the wave equation. Del square E equal to 1 over c squared del square E by del t squared. Okay, and what we are interested in, again, I'll write this, and you can get an exactly similar equation for the magnetic field. Do the same thing that I did for the electric field, and what you'll find is you'll get an equation like this for the magnetic field. Okay. So what we are interested in is, now I'll write the expanded form. So here's the general form of the equation. The electric field is, we're looking for electric fields that are dependent on x, y, z, and t, and that's equal to 1 over c squared del squared. So there is the blown up form. Okay. So what we'll do is we'll keep things simple. We'll look for solutions that depend only on x and t. Okay. So let's look for those solutions. So then this term will drop off, this term will drop off. And so what will happen is, so here will be our equation. Okay. 1 over c squared del squared by del t squared x. This is the wave equation, okay? And we're looking for solutions to this wave equation, okay? And you can solve these differential equations, and you'll have an exactly similar equation for the magnetic field. And so you'll have an exactly similar equation from the magnetic field. And here is a solution to this differential equation. E is E naught sine kx minus omega t. And where omega by k is equal to c, the speed of propagation of light. All right, so these are plane wave solutions, and this is what we're interested in. So you'll have a magnetic field equation for magnetic field similarly, and exactly same solution. Okay. All right, these are plane electromagnetic waves. So again, let me summarize this. So here are the 4 Maxwell's equations. Okay, so I'm going to erase this guy. So here are the 4 Maxwell's equations in vacuum. Okay, and these equations, if you study these equations predict the existence of this solution, which are plane electromagnetic waves. Okay, so from those equations, okay, from these 4 equations, Maxwell's equations in vacuum, we got this wave equation. Okay, and solutions to this wave equations. So here's the wave equations in 1 dimension. We're looking for plane wave solutions, and there is a solution. Okay, so those equations predict existence of such waves. Okay, and so when Maxwell predicted this, people went looking for these waves, and Mr. Hertz found these waves, demonstrated the existence of these waves. Okay, and so that's that's what we're studying. Okay, so there is the wave equation. Okay, again, this wave equation. So let me go back again. So what the wave equation does is, see, the wave equation is relating a second order spatial derivative to a second order time derivative. And dimensionally, c times t is distance. So you have distance square in the denominator and distance square in the denominator. Okay. All right, so there's the wave equation. So there's the wave equation that the magnetic field satisfies. Okay. And so there is the solution. There is the electric field changing with x. So here is the electric field changing with x. And as time goes on, this wave propagates to the right. Okay. And here is the magnetic field. It turns out that in an electromagnetic wave, the electric and magnetic fields are perpendicular to each other. And this this plane wave travels to the right. Okay, so let me show you this simulation of the electromagnetic wave. So there's the electromagnetic wave. Okay, and so this is the plane in which the electric field oscillates, and this is the plane in which the magnetic field oscillates. Okay, so let's get it going. And if you were standing here and measuring the electric and magnetic fields, see, this is what you will see. So the electric field at any location is changing with time. And if you, for a given time, if you go along the x-axis, the electric field changes. Okay. And that's what this, so that wave that you saw is a solution to this differential equation. And this solution is this fellow. Where is that guy? Okay, this solution is this guy. Okay, so this wave traveling is given by that expression. All right. So Maxwell, using his 4 equations, predicted the existence of electromagnetic waves. Okay, and so there are the 2 wave equations. Again, the wave equation relates the second order spatial derivative to second order time derivative. And like I said, C is related to the permeability of free space and permittivity of free space, like that. All electromagnetic waves travel at the speed of light, which is 3 times 10 to the 8 meters per second. Okay. So here are plane electromagnetic waves, which we wrote down, and see the electric field and the magnetic fields are perpendicular to each other. So there's the electric field, there's the magnetic field, and there's the direction of travel of the wave. And you can use your right hand and have your 3 fingers perpendicular to each other. And okay, you can have your right hand, and if your thumb points in this direction, your middle, your index finger points in this direction, your middle finger will point in the direction of the propagation, okay? And you're holding the 3 fingers perpendicular to each other. All right, so those are plane electromagnetic waves. There is the solution, there is the amplitude of the electric field, there is the amplitude of the magnetic field. K is the wave number, omega is the angular frequency, and the speed of light is frequency times wavelength, which is omega divided by K. Okay. All right, so here was Hertz's apparatus that demonstrated the existence of electromagnetic wave. This is how it looks. So this is almost 100 years ago, I believe in 1895 or something like that, so 125 years ago. This was the detector for electromagnetic waves. So what this device did is, this device, so you saw that in this simulation, to produce an electromagnetic wave, all you had to do was grab hold of a charge and jiggle it, okay? And one way of doing this is using an AC source and connecting it to 2 rods. Anyway, so to jiggle this, to make this charge accelerate, when the charge accelerates, it emits electromagnetic waves. And that's what this is. So you apply an AC volts to this, these are capacitors. And essentially the capacitors are, the polarity of the capacitor changes polarity, and that emits electromagnetic waves. You emit electromagnetic waves, and this is just an antenna catching the electromagnetic waves. So here's an AC source. This is an oscillating circuit. This is a This is an inductor. Okay, the oscillating frequency of this circuit is given by that 1 over omega square root of LC. Omega is 1 over square root of LC. So again, let me write it down in a form that you guys, so you guys, omega was 1 over LC. That's the oscillating frequency of that circuit. Okay. So the oscillating frequency, the resonance frequency of this is that. And if you take a source and pump energy at that frequency, you can pump a lot of energy in there. This AC signal couples via transformer to this inductor, which is connected to a capacitor. And this guy, so as you send an AC signal to this, this will become positive, negative, and switch back and forth. And this guy will emit electromagnetic waves. Here's another capacitor that gets charged, and that's where you detect the electromagnetic waves. So in 1895, this was first done by Mr. Hertz. Okay, so you're transmitting energy across pure space. Okay, so this is electromagnetic waves. Okay, so there are the apparatus. All right, now we'll study some properties of electromagnetic waves. So, but let me pause here a second, and I will let you guys ask questions.